Okay, so we're in chapter 4 now, and chapter 4 is concerned with applications of the derivative. We have so far done a lot of work with the derivative, and we've looked at some applications back in chapter 3. But our primary, well, I shouldn't say our primary, we have a couple of things we're going to do in chapter 4, but one of the main goals in chapter 4 is working towards something that we call optimization. And so section 4.1 is sort of a key section in getting us there. So what we're looking at in section 4.1 is what we call maximum and minimum values. And specifically, if you have a function, y equals f of x, for example, we are looking for the maximum and minimum, or largest and smallest values that function can attain under certain conditions. So that's a little bit vague, but to motivate this, there's plenty of examples in real life where you would want to optimize a function. So I give a couple of examples here. A company obviously is going to want to maximize its profit, but if you think of profit as a function of, say, man hours, labor, that's something that you would want to maximize. What is the ideal level of labor or man hours that a company should utilize in order to maximize its profit? So calculus can help us with that if we're able to come up with a function that does such a thing. Or another example that we're going to look at, minimizing the area or maximizing the area of a rectangular enclosure with a fixed length of fencing. Maximizing is actually the more typical case that we'll be looking at there. But these are just some examples. We'll look at a lot more later on in chapter 4. In order to make much sense of this stuff, we need to come up with some definitions for the terms we're going to be using throughout chapter 4. So the first definition we want to talk about is absolute maximum and absolute minimum. If c is some number in the domain of a function f, and we're going to denote capital D, or use capital D to denote the domain of that function, then f of c is called the absolute maximum value of f on the domain D if f of c is greater than f of x for all x in D. One thing to point out about this, the maximum is an output of the function, not an input. So f of c is whatever you get from plugging c into the function f, giving you an output. And what this is saying is that the absolute maximum is the largest output of all the possible outputs of that function over its domain, whatever its domain happens to be. That's what this inequality is saying. F of c is greater than or equal to all of the other outputs of this function. Absolute minimum is similar. An absolute minimum value of f on our domain D is a value f of c where f of c is less than or equal to f of x for all x in the domain D. So that would make it the smallest output on that domain. Now, we sometimes refer to these as global extrema, global maximum and minimum values. That's an interchangeable term with absolute maximum and absolute minimum. And together we refer to these as extreme values, or if we want to use an alternative term, extrema. So extrema is plural. Okay? We'll be using that term a lot. Now, absolute maximum and absolute minimum are one type of maximum and minimum value that a function can attain, but we also talk about another kind of maximum and minimum value, another kind of extrema. And these are local maximum and local minimum values. And we'll look at some graphs to sort of see the difference between those two things. But to define this, we say that a number f of c is a local maximum value of f if f of c is greater than or equal to f of x when x is near c. So notice the inequality is the same inequality that's used in the absolute maximum value, but now we're not looking at f of x for all x in the domain of that function, which is everything you can plug into it. We're only looking at values that are close to this number c. And a more accurate term would be an open interval surrounding C, or an open interval containing C. A local minimum value of f is a number f of c such that f of c is less than or equal to f of x when x is near c. So again, not necessarily for all x in the domain of f, but at least for those values of x that are close to this number c, f of c is the smallest value in that little neighborhood. Neighborhood is actually a term that we use in higher levels of math to describe this concept. Okay. So I want to look at a couple of examples here. This graph, we don't have an algebraic form for this function, but in this graph I have a few values denoted A, B, C, D, and E along my x-axis. And these maximum and minimum values, whether it's absolute maximum or minimum or local maximum or minimum, are outputs. Now if you notice, a couple of values are denoted here, f of A and f of D. F of A would be the y value of this point right here. And I can see that this point is the lowest point anywhere on the graph that's shown here. Right there is the lowest point. That means f of A is the smallest output in this entire function. If we think of everything that's shown as representing the entire function, that would make f of A an absolute minimum. Okay, it's the lowest point, or it's the smallest output anywhere that I can see on this graph. F of D, for comparison, is the highest point. So, or this point right here is the highest point on this graph, which means f of D is the largest output. That would make this an absolute maximum. Okay? What about these other points that are shown here, though? Here, here, and here. None of these are absolute extrema because we can find values that are both larger and smaller than the outputs of those points on this graph, but they are local extrema because if you look at a small interval around B and you look at all the points on the graph corresponding to the values in that interval, this point is the highest point in this small window, this small interval that I've created. That's what makes it a local maximum. It's the highest point within this little window. Same thing with f of c. If I put a small interval around f of c and only look at the points on my graph corresponding to those values, I can see that f of c is the smallest output of all of these points. And then similar for f of d. If I put a small interval around D, I can see that f of D is the highest point. Now we've already said that f of D is an absolute maximum, but it's also a local maximum for that reason. I could do something similar with f of E. I can see it's the lowest point in that small interval. This graph shows that a little bit better. So in this graph here, this blue curve is another function that we're looking at extrema for. And if you look at these points, I, j, and k, these are intervals, I, j, and k that it's creating. Even though each of these points, or at least let's look at these two. These 2 points are neither the highest nor lowest points on the entire graph. They are the lowest and highest points within a small interval surrounding those values. So, for example, f of 4, if this function is called f of x, f of 4 is going to be the smallest output within this small little section of that curve. Similarly, f of 8 is the highest or the largest output in this particular little interval. Same thing here. This value here, f of 12, I can see is the lowest point in this small interval. And not only that, it's also the lowest point in the entire part of the curve that's shown. So that makes it both a local and absolute minimum. Okay? So we're going to take a look at an example here. For each of these values, A, B, C, D, R, and S, I want to state whether the function has an absolute maximum, minimum, local maximum, minimum, or neither at each of these points. Okay? In particular, remember the maximum and minimum values are the outputs that correspond to these points, not the inputs. So f of A, f of B, f of C, and so on. Those are the values that we're interested in. Okay, let's start with f of A. F of A is this point right here. And it looks like f of A is a minimum because it's a low point compared to points around it. So I would say that f of A is a local minimum because if I put a small interval around it, all of the points contained in that interval are larger than all of the outputs of these points are larger than f of A, making f of A the smallest value in that interval. But also, if I look at any other point on this graph, f of A appears to be lower than all the other points along this curve. So I would say that f of a is both a local and absolute. I keep using ABS to abbreviate absolute. I'm going to do that a lot. Minimum. Okay? Now what about f of b? Well, even though at first glance you might think f of b is here, there's an open circle there. F of b is actually this, the output of this point right here, the y-coordinate of that point. And looking at this point, is this point an absolute minimum or maximum? Well, it's definitely not an absolute minimum because it's higher than the point that we've already identified as having an absolute minimum. So it can't be that. Is it an absolute maximum? No, there's other points, namely right here, on this curve here, that are higher than that point. So it can't be absolute maximum or minimum. Is it local? Well, let's put a little interval around it and focus on the points in that interval. This small little interval, the way that I've drawn it, it actually does look like this point is the highest point anywhere in that interval. So I would say that f of b is a local maximum. Okay? What about f of c? F of c is this point right here. It's definitely not a local maximum or minimum because I find points that are higher and lower than that point. So let's look at local. I put this little interval around it, and I can see that some of the points in this interval would exist up here, which are higher than that point, and some of the points in this interval exist down here, which are lower than that point. So it doesn't appear to be a local maximum or minimum, but maybe I just didn't make my interval small enough. Well, it shouldn't be too hard to see that no matter how small I make this interval about c, I'm always going to have some points that are lower than f of c, or some outputs that are smaller than f of c, and some outputs that are larger than f of c. So there's no way it's going to be a local extrema either. F of c is neither. Okay, what about f of d? Looking at f of d, I would say it's definitely not an absolute max or absolute min. Again, we have lower and higher points than this one. But is it local? Is it a local extrema or a local extreme? It appears to be a local minimum because where I've drawn this point, if I put this small interval around d and then look at all the points that correspond to the values in that interval, they all appear higher than d except for f of d itself. So f of d appears to be a local minimum. Okay, two more to go, f of r and f of c. Looking at f of r, that's this point, that's the y value of that point right there. It's definitely a local maximum because again, if I put an interval around that point, that appears to be the highest point on the graph within that interval there. But it also looks like it's an absolute maximum because I can't find any points anywhere else on this graph that are higher than that one. So I would say that f of r is a local, local and absolute maximum. Okay? Finally, let's look at f of s. F of s is not an absolute minimum because it looks like it's just slightly higher than this point here that we've already identified as having an absolute maximum for its output, or minimum, sorry, not maximum. But I think it is a local minimum because if I put an interval around it, it's the lowest point anywhere in that interval. So that would make it a local minimum. Okay? So when we have a graph to look at, it's not too hard to identify these things, especially after you've done one or two problems like this. All right. Here's another example. We want to find the local and absolute extrema of y equals cosine of x. Now, in the homework for this section, you might be given a problem like this, and you wouldn't be given the graph. You'd have to come up with the graph yourself. And so rather than me make a sloppy handwritten graph, I just went ahead and pasted it in there. The cosine function we know has a maximum and minimum values of 1 and -1 respectively. And it is a periodic function, so it keeps alternating between those maximum and minimum values. But I can see here that both the local and the absolute maximum and minimum values are found at these points here. So the local and absolute max is 1. Remember, it's the output of these points only. It's not the entire point, so it's not the ordered pair, and it's not the x-coordinate either. It's the output that we're talking about. Similarly, the local and absolute minimum would be -1, because the -1 is the smallest output I'm getting anywhere along this function. And the point of showing this example is to kind of just remind you or emphasize the point that even though a function can only have one absolute maximum and one absolute minimum, it can occur at several points on the curve. So the local, sorry, I shouldn't have said local. It can only have one absolute maximum and one absolute minimum, any function. But that same maximum or minimum can occur at many different points. So the absolute maximum of the cosine function is just 1. It's the only absolute maximum that it has, the number 1. But it occurs multiple times on that function. Okay? Similar with the absolute minimum of -1. Okay, so now that we've gotten some of that terminology under our belts, let's talk about the extreme value theorem. We sometimes refer to this as the EVT for short. The extreme value theorem is an extremely important theorem in calculus because it's what guarantees that we can optimize certain types of functions. And here's what it says. If f is a continuous function on a closed interval a, b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in that interval. So these graphs here are kind of showing you the extreme value theorem at work. It's extremely important to know what kind of functions this applies to. Only functions that are continuous on a closed interval. And you're going to see throughout chapter 4, we're going to be looking at closed interval subsets of the domain of f. Okay, f may be defined elsewhere as well, but we're restricting our attention to some closed interval on the x-axis. So here's an example of a function that's clearly continuous. I can go from this point to this point along that curve without picking up my pen. Okay, and the extreme value theorem says that as long as we know that this function is continuous on that closed interval a and b, I am guaranteed to have an absolute maximum and an absolute minimum occur somewhere in this curve, on this curve. I can see here that c gets me to my absolute maximum, so f of c would be my absolute maximum. F of d appears to be my absolute minimum. It's the lowest point that I can find. Here's another example. On the closed interval from a to b, I have this function. Notice that this absolute this absolute minimum, which occurs at this point right here, happens to also be one of the endpoints of that function. So we can see that sometimes absolute extrema occur at an endpoint. And when I say endpoint, I mean at an endpoint of the interval a, b. So that's why it says d equals b here. D is where the absolute minimum occurs, but it happens to be f of b. F of c, I can see, is giving me the largest output of all the points on this curve, so that would be my absolute maximum. And then once again, here's another example where you can find the maximum value and the minimum value, and just like the cosine function, in this case, the absolute maximum occurs in two separate places, f of c1 and f of c2, because these 2 points we're assuming are the exact same height. So again, even though the extreme value theorem guarantees an absolute minimum and an absolute maximum, it doesn't mean that it only occurs at one place for each of those extrema. Okay. Down here are a couple of examples of graphs that we want to look at to show why the assumption of continuity on the interval matters for the extreme value theorem. Because again, the extreme value theorem says if f is continuous on a closed interval, then we can find these absolute extrema on that interval. Okay, so here's an example of a function that is not continuous. It has a jump discontinuity. This function, even though it does have an absolute minimum right here, has no absolute maximum. And why is that? Well, it looks like the highest points on this curve are found on this branch of it once we get up here towards this open circle. But that is an open circle, isn't it? So that means there's no actual point there. So what then would be the highest point? Well, if you know much about the real numbers, you know that you can't find a real number that's right next to another real number, because you can always average those two and get something that's in between them. So what that implies here is that there is no highest point here, because if there were, it would have to be the point that's just below that open circle, such that no other points are between them. But that's an impossibility in the real numbers. So that's a little bit tricky to wrap your mind around if you haven't thought about the real numbers in that way before. But this function has no absolute maximum. It does have an absolute minimum. This function right here has neither an absolute minimum nor an absolute maximum. There's an open circle here, so that's the same issue that we had here. So no absolute minimum, because we have points that are getting closer and closer to this, but no actual lowest point anywhere. And then this function is asymptotic. It has an asymptote at x equals 2. So remember, vertical asymptotes are a type of discontinuity. And this function is not going to have an absolute maximum, because this function keeps going higher and higher and higher. It doesn't stop anywhere. Okay? So those are a couple of cases kind of illustrating why we need that assumption of continuity for the extreme value theorem to work. Okay, I think I'm actually going to save this for part 2.